For most of the rest of the semester, we're going to be talking about quantum physics. It's an amazing story. But what I want to do here is to tell you where that story came from. Why did physicists feel obliged to change their ideas about matter and energy so completely near the beginning of the 20th century? So that's the story we're going to tell. And it's part of an immense story, a huge story that spans the entire history of our thinking about the natural world. Essentially, it all goes back to one fundamental question. Is the world made up of stuff or things? That is the fundamental nature of the objects in the material world continuous or discrete? So, for example, let's think about the nature of matter. Since at least the time of the ancient Greeks, there have been two competing schools of thought. One school of thought is represented by the Greek atomists, like Democritus. And the atomists believed that the nature of matter was as an assembly of very tiny indivisible particles called atoms. In fact, the word atom means indivisible. And everything we see in the world is made of little atoms. And the whole universe is made up of nothing but atoms and the space between them. Or as they would say, atoms and the void. And every phenomenon that we observe has to do with the motions and the combinations of the atoms. On the other hand, there were other philosophers, such as Aristotle, who thought that this wasn't right. That Aristotle did not believe in the concept of completely empty space. He said there was no void. And so matter for him was a continuous substance that filled the space of an object. Or consider the nature of light. In the 17th century, there were two competing notions of the nature of light. Isaac Newton believed that light was made out of discrete little particles, light corpuscles, he called them. And so light was fundamentally thing-like, discrete, made of discrete light corpuscles. His contemporary Christian Huygens believed that light was a wave phenomenon like sound. We already knew that sound was made of vibrations in the air, propagating as waves. And Huygens said maybe light is the same. But in the 17th century, they were unable to decide between the two hypotheses. Then, about the year 1800, natural philosophers, that's what they called physicists in those days, made a series of discoveries that really revolutionized their understanding of the nature of matter. They found that a great number of chemical and physical phenomena could be explained by the old atomic theory of Democritus and the atomists. So, for example, the ratios of materials in chemical compounds could be explained if the atoms were combining in certain discrete ways. So, for example, you would have two hydrogen atoms and one oxygen atom forming water. But you never had 2.5 hydrogen atoms or 1.5 hydrogen atoms. A certain amount of hydrogen would combine with a certain amount of oxygen. And with the same kind of hypothesis, you could explain facts that they noticed about the volumes of gases, or the kinds of crystal structures that you could observe in solids. Crystals are spatially regular arrangements of atoms, and only certain spatial arrangements are possible. And later on in the 19th century, they had even more evidence for this view of matter. For example, they could explain the properties of certain substances by considering molecular structure, the spatial arrangements of the atoms inside the molecules composing a compound. And they could explain the properties of heat by regarding the energy of heat as really energy of microscopic motions of the molecules. So in the 19th century, we came to the idea that matter is made out of atoms. Matter is fundamentally made of things. It's thing-like. But at about the same time, there was an enormous discovery about light that we've already talked about. Young's two-slit interference experiment and subsequent experiments about diffraction pretty much established that light was a wave, that Huygens was right and Newton was wrong. Light is some kind of wave phenomenon. In those days, they thought that there was perhaps some continuous substance called the ether filling all of space, and that light was a kind of wave in the ether. And later in the 19th century, James Clerk Maxwell realized that light was an electromagnetic wave. The wavy stuff was the electromagnetic field. The point is that light is continuous. It's stuff-like, wavy stuff, but continuous. So that's the 19th century synthesis. Matter is discrete and made of atoms. Light is a continuous wave phenomenon of electromagnetic fields, or possibly disturbance in a continuous ether. We've already talked about some of the revolution around 1900. The first problem, of course, was the problem of the Michelson-Morley experiment, which indicated that our ideas about light as a wave in the ether, our ideas were wrong. And it took Einstein in his special theory of relativity to show how we could come up with a theory in which the speed of light was constant in every frame of reference, independent of the motion of the source. And that theory involved far-reaching changes to our ideas of space and time. So the Michelson-Morley experiment was the first experimental puzzle that led us to embrace radical new ideas about the universe. But now it's time to talk about the second puzzle. And the second puzzle was the puzzle of blackbody radiation. So what do I mean by a black body? Well, every warm object emits thermal electromagnetic radiation, electromagnetic waves due to its thermal energy content. And it turns out that objects which are very good absorbers of radiation are also very efficient emitters of radiation. And that's because the emission and absorption process are just the reverses of each other. So a substance that's really good at one process at a given wavelength would be also good at the other process at a given wavelength. All right, that means that the most perfect kind of emitter of thermal radiation would be a black body, one that is a perfect absorber of thermal radiation. And there are objects that are approximately black bodies, like a piece of charcoal or something would be a good black body. But in fact, you can make a good black body out of almost anything. The idea is this: take a block of some material and then dig a hole in it, have a little hole at the outside and a hollow cavity inside the block. Now, light that goes in the hole may bounce around a little bit, probably gets absorbed by the block, even if the material is not very absorbing. And so that means that that little hole opening into the cavity looks black. It doesn't reflect light away from it. So if that hole into the cavity is a good absorber of radiation, it will also be an ideal emitter of radiation. So if I heat up that block of material, the electromagnetic radiation coming out of that hole, out of the cavity, will be like that of a nearly perfect black body. And all black bodies, and therefore all cavities, will radiate exactly the same way, no matter what the material is. In the last couple of years of the 19th century, the problem of blackbody radiation, cavity radiation, attracted the attention of the German physicist Max Planck. Now, Planck was brilliant, not least because he understood how to pick a significant problem. Every kind of material will produce the same kind of cavity radiation. Every kind of black body produces exactly the same radiation at a given temperature, the same intensity of radiation, the same mix of wavelengths. And so that means if you understand black body radiation, you've understood something of universal importance, something that applies to all kinds of material. So, Planck decided to think about black body radiation. Now let's follow Planck's footsteps. Then we'll start with the ideas of classical physics, the physics of the 19th century, the 19th century synthesis in which light is a continuous wave and matter is made out of discrete particles, atoms. In classical physics, at a given temperature T, that's absolute temperatures, which we might measure in kelvins, at that temperature T, any oscillator, any oscillating molecule or whatever, any oscillator will on average have an energy of Kb times T, where Kb is a constant called Boltzmann's constant, after the Austrian physicist Ludwig Boltzmann, and it's got a very small value, 1.38 times 10 to the minus 23rd joules per Kelvin. So the thermal energy that an oscillator has at a given temperature is a small amount, but it may only be a single molecule, so it may be moving around pretty fast. Anyway, kBt is the amount of energy that an oscillator has, on average, at a given temperature. But what if we apply that to light? The light waves in an enclosure, like the transverse waves on a wire, are made up of a combination of standing wave patterns. So with the wire, we have the fundamental and the second harmonic and the third harmonic, and every wave motion of that wire with the fixed ends is a combination of those standing wave patterns. And each standing wave pattern oscillates independently of the others at its own frequency. So if we think about that for light, each standing wave pattern of light in 3 dimensions, so there's lots and lots of these standing wave patterns, each standing wave pattern of light at a given temperature should have the same energy on average, that Kb times T, the thermal oscillator energy. That should be the energy of vibration of each standing wave pattern of light in an enclosure like a cavity. So here's the problem. There are a lot of standing wave patterns for light. In particular, there are a lot of short wavelength, high frequency standing wave patterns. There are way too many of them for this to be true. So think about it. You can have a wavelength of light as short as you like. So that means that there are an infinite number of possible wavelengths of light in an enclosure. And if every one of those standing wave patterns, every one of those wavelengths, is going to have the same small amount of thermal energy on average, then the energy in the thermal radiation should be infinite. The problem is these short wavelengths. I mean, there are a few long wavelength standing wave patterns, but there are more and more and more of them as we go to shorter wavelengths and higher frequencies. And so that means if you were to plot the energy in the light intensity, as a function of wavelength, then over it for long wavelengths, you'll have a small amount of energy. And then as the wavelengths get shorter and shorter, there are more and more standing wave patterns, so the energy it goes up, the light intensity goes up, and at shorter and shorter wavelengths, it goes up even further, and it diverges as the wavelength goes to zero. There are just too many short wavelength standing wave modes of light for each of them to get the same little amount of thermal energy on average. This problem is called the ultraviolet catastrophe. If you just take what we know about the nature of heat and what we know about the wave nature of light, and you try to put them together, you predict that thermal radiation should have an infinite intensity. In particular, it should have really high intensity at short wavelengths. Now, this isn't what really happens. What really happens is that curve of intensity as a function of wavelength is small for long wavelengths, and then it goes up, but it reaches a maximum and bends back down for short wavelengths. There's very little electromagnetic thermal radiation at very short wavelengths. So how could this be true? That's the problem that Planck sets himself to solve. By the way, that curve of light intensity as a function of wavelength is called a spectrum. In this case, it's a continuous spectrum. All different wavelengths contribute to the light being emitted by a warm object. And so Planck's problem is the problem of explaining the spectrum of blackbody radiation. Planck found that he had to assume that the energy of light came in discrete, indivisible amounts, what he called light quanta. That's the quantum in quantum theory. They later came to be called photons. Well, let's call them light quanta for now. That you could have 0 quanta, or 1 quantum, or 2 quanta, or so on, but you couldn't have 3.75 quanta of light of a particular frequency. And the amount of energy in 1 quantum of light depended on the frequency of the light. It was proportional to the frequency. So high frequency, short wavelength light had high energy quanta. Long wavelength, low frequency light had very low energy quanta. And that means that the equation is E, the energy of 1 quantum, is equal to h times f. H is a constant that we now call Planck's constant, and it's really, really small. It has a value of about 6.626 times 10 to the minus 34th joule seconds. So it's really small. 1 quantum of light is really, really tiny. The light overhead is producing millions of trillions of light quanta every second. But light can only transfer energy in discrete amounts. Now, interestingly, Planck himself realized how radical and important this idea was. He told his son on the very day that he thought of it, he said, "Today I've come up with an idea as important as the idea of Newton." Now, if you've ever made even a small discovery in science, you sort of know that feeling that this is tremendously important. But in Planck's case, he was exactly right. This was as important as the discoveries of Newton. So how does Planck's wacky quantum hypothesis solve his problem? How does it explain the spectrum of blackbody radiation? How does it prevent the ultraviolet catastrophe? Well, here's how it works. If you're talking about light at very high frequencies, where the ultraviolet catastrophe might take place, if the frequency of light is such that Planck's constant times the frequency is much greater than Boltzmann's constant times the temperature, then there's not enough thermal energy even for a single light quantum to be produced in the radiation. There's just not enough thermal energy around even to get one photon. And that means instead of having a typical amount of thermal radiation, thermal energy in that mode of radiation, you'll have more like no energy in that mode of radiation. There's less energy expected at high frequency, short wavelength, standing wave patterns. So there's no ultraviolet catastrophe. And in fact, Planck is able to reproduce, theoretically, all of the details of the blackbody spectrum. How it depends on temperature, how it depends on wavelength. And it all boils down to this one hypothesis, that the energy in the continuous light waves is somehow discrete. The consequences of this are mind-bending. Somehow, the fact that light is a continuous wave, which we know, which we verified in the two-slit experiment and a score of other experiments and demonstrations about the wave nature of light, somehow the continuous wave nature of light, the way light propagates through space, doesn't prevent it from interacting with matter by exchanging discrete amounts of energy, discrete quanta, discrete photons. When we think about how light moves through space, it's a continuous wave. When we think about how light exchanges energy, it's as if it's made of particles. So how does that work? What are the implications of that? Well, we're just at the very beginning of a terribly important story. And the next chapter of that story will be written by our old friend, Albert Einstein. In one of his other 1905 papers, about the same time he's inventing special relativity, he's also taking Planck's quantum hypothesis and explaining many more phenomena about light that were, up until that time, a little bit mysterious. But that's where we'll start in class.